This video describes our ability to control force. Normally during the day we don't exert maximal forces to a great extent. That is, we don't have to exert really high forces as we would in a sporting event. If you're a football player, you're a weightlifter, you might have to activate all your muscles in order to lift a very heavy weight. But most of the activities we do during the day involve the fine control of motor output. So if you are going to stroke your baby's cheek, you don't want to smack the baby in the face. You want to do it nice and smoothly and with very low forces. So how do we control those forces? In order to fully activate all the muscles, typically we think all we have to do is think about it. Have our brain send down a strong signal to our motor neurons, activate all those motor neurons, which would activate all the muscle fibers, and we get a very strong contraction. But it's not as simple as that. Although the brain does have a very strong input into the motor neurons, there are a lot of peripheral afferents working as well. So a lot of information coming from the muscles and the skin and various other parts of the body that will either excite or will inhibit our ability to activate those motor neurons. So for example, if I wanted to lift the heaviest weight I possibly could, obviously I'd psych myself up and send a strong signal down from my brain or the supraspinal centers. Now, while I'm doing that, there's information coming from the muscles. So for instance, the muscle spindles, which are the stretch receptors in your muscles, if we activate those and we stretch the muscles, they'll send excitatory inputs back to the motor neuron. So they'll excite the motor neuron. So they'll help to excite more motor neurons to make us even stronger. So as we had in another video where I showed that if we did a counter movement jump and moved our body rapidly and stretched the muscles, or if we did a myotatic stretch reflex where we hit the tendon and the leg or the arm moves up, then that's an example of how we excite those motor neurons. And the muscle spindles, or the stretch reflexes, can contribute up to 30% more activation in addition to what your brain can do. So you can get much more force applied from that peripheral activation. Now, in addition to that, we've got inhibitory centers. In your tendons, you have what are called Golgi tendon organs. Now, a Golgi tendon organ detects force. And so it's there to protect the muscle. Because if we have too much force in the muscle, we may tear that muscle and injure the muscle. So the Golgi tendon organ detects how much tension, and as the tension goes up, it sends signals back to the spinal cord to inhibit it, to kind of turn it down. You can almost think of the Golgi tendon organ as a P inside of a rubber band. And as a rubber band is being stretched, that P gets squeezed. And as you squeeze that P, or Golgi tendon organ, it's sending inhibitory signals back. So you've got the stretch receptors trying to activate, the Golgi tendon organs trying to inhibit. Now what about the joint? Well, we did research back in the 90s where we examined the ability of individuals who had fractured their ankles. What was their ability to activate their muscles? And we looked at two groups of people. We looked at people that had fractured their ankles and all they had to do was put a cast on it, and within 3, 4, 5 weeks the bone mended together and they were back on the road. There's other people that had more severe fractures. And these people would have to go in, and they're called fixated fractures. So in this case, they'd have screws or plates put on the bone to keep them together. And what we found was that even 2, 3, 5, 6 weeks after getting out of the cast, that anybody who had an ankle fracture had a diminished ability to fully activate their muscles. And if you had to have a fixated fracture, that is a screw or plate, then your ability to activate those muscles was even less than the people who didn't need fixation. So they just had a cast. So why would that happen? Well, the reason that happens is that your joint has receptors as well. And they tend to detect whether the joint is in proper alignment. So if the joint is not in proper alignment, it'll send negative signals or inhibitory signals back to the spinal cord. And so other research has shown that even a year and up to 3 years afterwards, if you have a fracture, that you still have problems fully activating your muscles. Because if that joint isn't in alignment, there's always inhibitory signals going back. And then if you fractured your ankle and you're experiencing pain from swelling, well, pain is also inhibitory. But what we found is that pain is very individualistic. Some people can handle pain better than others. So we found in our studies that athletes who are accustomed to having pain whether it be from football and getting hit or from injuries, they were better at activating their muscles than the ordinary citizen on the street who's not accustomed to getting hit and receiving pain. So there's a lot of different factors, and in order to be able to fully activate your muscles, you have to pull all those factors in and get as many excitatory inputs as possible. So you want your brain to excite the spinal cords. You want your muscle spindles to excite the spinal cords. You want to make sure your joints are properly aligned. You want to try and not have Golgi tendon inhibition. So if we can bring all those factors together, then perhaps we can fully activate a muscle. Now, like I mentioned before, though, we don't often need to fully activate a muscle. How often do you go during the day and fully exert? How often do you try to lift as much weight as possible? How often do you try and run somebody over like you would in a football game with full power? No, most of our day is spent working on a computer, so very low forces, writing something down, very low forces. Even if you're going to hug somebody that you like or love, you're not going to try and squeeze them to death. It's going to be low forces. So most of our system is made up so that we can control our forces and have smooth forces, and that we're very, very coordinated. So how does that happen? Well, if we think about how the motor neuron works, it's an all or none phenomenon. So if you consider one motor neuron and you send a signal to activate that motor neuron, all the muscle fibers attached to that motor neuron will automatically contract. It's an on and off system. There's no in between. So if we just relied on activating those motor neurons, then we'd be like robots. Things would turn on and they turn off, on and off. And that's not very coordinated, nor is it very smooth. So we have to find ways to do that. So the first thing that we do is we use recruitment in order to recruit various levels of motor neurons. If you remember, we have slow twitch motor units and we have fast twitch motor units. Slow twitch motor units, when we turn on a slow twitch motor unit, we normally will add about 3 to 5 grams of force, so a very small amount of force. So let's say I turn on motor unit A and we get a jump in force. Now, I think I need a bit more because I want to stroke my baby's cheek, but with only one motor unit on, she can barely feel it. So I turn on another slow twitch motor unit, and I have another 3 to 5 grams of force. But as I keep on turning on more motor units, the jumps are higher. All right? So we've got C might be slow twitch, but maybe D might be fast twitch. Now, fast twitch can add 10 times more force than the slow twitch. So if I try to turn on the fast twitch, then I'm going to be jumping by 30, 50 grams, or 100 grams. So again, if I'm stroking my baby's cheek and I'm just going from 3 grams, turn on B, I go to 6 grams, I turn on motor unit C, I go to 9 grams, but then all of a sudden I turned on motor unit number Z and I turn on an extra 200 grams, I go from here to smuck. Now I don't want to smuck my baby's face. So what I have to do is I have to control. Now the problem is I've got these jumps, and each jump is a fairly significant jump. So now what the system wants to do is it wants to try and modulate that jump. What you want to think of is that your system is like a stereo system. In your stereo system you have an amplifier. In fact, if you've got a really expensive system with big speakers, you might have 2 amplifiers. So what I'm going to do is I'm going to turn on one amplifier and a second amplifier and a third amplifier to get those motor neurons working for me. But your amplifier also has a volume switch. So when I turn on my amplifier, I don't want it to go from 0 to full power. I want to turn it on so I can go from, let's say, from number 1 to number 10. And so I can modulate the power of my amplifier. So the next step is called rate coding or firing frequency. And with rate coding or firing frequency, now what I can do is I can turn on my motor neurons at different frequencies. So normally when I'm going to turn on a motor neuron, it might turn on at 5 to 10 hertz. So that's 5 to 10 stimuli per second. So now rather than jumping from here to here, I can make it smaller jumps like this. And then when I need the next motor neuron, then again, I won't turn it on completely. I'm going to turn it on with my volume switch or my rate coding. Right? So now I've got smaller increments. Rather than this big increment, I've got these smaller increments that I can turn them on. The good thing about using more slow twitch fibers as well, or motor neurons, is that they have greater afferent stimulation. They receive more information from the environment to come back. So once again, when I'm touching my baby's cheek and I'm just using slow twitch fibers, I get a lot of information coming back to my spinal cord and my brain telling me how hard I'm touching my baby's cheek. Whereas the fast twitch fibers don't provide you with as much information. I don't need that information if somebody is attacking my baby and I want to punch them out. I don't need to know whether I've provided 3 grams or 4 grams of force. I just want to provide maximum force against that person's head who's attacking my family. So it's not as important with fast twitch fibers to have that feedback. Another thing with slow twitch motor neurons is you have a greater innervation, or a lower innervation ratio. What does that mean? Well, lower innervation ratio means if I have motor neuron A and it is attached to a bunch of slow twitch fibers, the number of fibers it's attached to will be much less than the fast twitch fiber, let's say, or fast twitch motor neuron D. So, for example, you might have 1,000 fibers that are attached or innervated by motor neuron D, whereas the fibers that are innervating my eye, which are slow twitch fibers, because I have to move my eyes all day long, it wouldn't be good if they were getting tired, I might have 3 to 5 muscle fibers. So 3 to 5 muscle fibers to each eye muscle. So I have very, very fine control of my eyes. But I would have 1,000 going to my biceps or my quadriceps. So every time I turn on a motor neuron to my biceps or my quadriceps, I have a big jump in force. So you're certainly not as coordinated with the big muscles as you are with your eye muscles. So for example, you play the piano with your fingers. You don't play the piano with your knees. Because again, your hand muscles have a lower innervation ratio, so they're much better controlled and they have better afferent stimulation than your quadriceps and your hamstring muscles. So we talked about recruitment. We talked about rate coding. What we also need to do is when we activate the muscles, we activate them in an asynchronous manner. Now what does that mean? Well, if I was going to activate all my motor neurons in a synchronous manner, it would go like this. I'd have no force. I'd turn on a motor neuron. I get some force. It relaxes. I get some force. It relaxes. I get some force. There's motor neuron A. Motor neuron B, if they turn on synchronously, meaning turn on at the same time, then I would get B, force, relax, force, relax, force, relax, force. And we'd continue on, C, D, etc., etc. So what kind of force would I get? Well, I would be like a robot. I turn it on and turn it off. Turn it on, turn it off. If I was trying to feed myself, I'd end up throwing the food past my head or throwing water in my face because I'd have no control. So if we do it asynchronously, then I turn on A. Now B would turn on slightly later. So here's B. B turns on slightly later than A. C turns on slightly later than B. D turns on slightly later than C. Now, before we saw the forces going up and down. Let's look at the force here. There's slight deviations in the force, but for the most part, it's fairly smooth. So I'm holding my hand here. It's not jumping up and down because it's not synchronous. It's not turning on and off. It's asynchronous. It's smooth. I'm writing my name. It's very smooth. So it's an asynchronous stimulation that's being controlled by both my recruitment and the rate coding of my slow twitch fibers to allow me to be very, very smooth. Now there's another aspect. The motor neurons have a mechanism that we call the disfacilitation of previously activated motor units. What does that mean? Well, let's go back to here. If I turned on motor unit number A, and motor unit number A gave me 3 grams, and then B gives me 3 grams, and C gives me 4 grams, and D gives me 5 grams. Well, I'm jumping up from 3 to 6 to 10 to 15 grams every time I turn on a new motor neuron. What the system does is that when you turn on B, B tends to inhibit A. C tends to inhibit B. D tends to inhibit C. So instead of having 3, 3, 4, and 5, you would turn on A at 3, but when you turned on B at 3, it actually turns this down to 1. You turn on C at 4, that'll turn that down to 1. You turn on you turn on D at 5, that turns that down to 2. Now I'm just making up these numbers just to make a point or the concept, but now rather than having 3, 6, 10, 15 grams, we now have 1, 2, 4, 5, we have a jump of 9 grams. So you can see that the system is not made to allow us to exert the highest forces. The system is made to try and allow us to have smaller and smaller increments. So once again, you can think of the system as your stereo system. And you've got a better stereo system, you have more control over how that volume is coming out. And that's what our system does. Now on top of that, again, your muscles, the muscle spindles that we spoke about, have proprioceptive capabilities, meaning they can tell you where you are in space. So once again, when I'm stroking my baby's cheek, I know how far my muscle has moved or my joint has moved because the muscle spindles tell me that. And the Golgi tendon organs tell me how much force has been exerted. So you can see how all this information is always being fed back to the central nervous system to help us control how much force is being exerted. And mostly, we want to try and have fine forces. In order to get maximal forces, whether it's because of athletic activities or because of a fight or flight mechanism, we have to protect our family, then we have to overcome all these inhibitory mechanisms to try and activate the muscles. And that's why it's so amazing to see high-level athletes doing their thing, because they have taught their body how to overcome all these inhibitions and provide themselves with the greatest amount of force possible. So, maximal forces, submaximal forces, all involve excitation and inhibition. It's not just from the brain, it comes from the whole body, and it's our job as either the average person or the athlete to be able to inhibit in order to get smooth control or to activate to get maximal control.